We're going to take a look at how we represent lines and planes in a three-dimensional area or in space, so to speak. So let's take a look at how we draw a line in 2 dimensions. A line in 2 dimensions, generally we have to have a point that we want to go through, and we have, let's call that x1, y1, and generally we have the slope of the line. And we can write this equation as y equals mx plus b in general, where we have a point that is a y-intercept over here somewhere, and the slope. But to be able to write the equation of a line, remember you need a point on the line and my word slope has way too many L's in it, and the slope of the line. So that's going to be pretty close to what we need in 3 dimensions as well. So let's talk about something like this. Let's say that we have a point we know we want our 3-dimensional line to go through. So this is going to be our x naught, y naught, and z naught. So that's a specific point. And let's just for fun go ahead and draw a line. Let's see here. If I pick some other random point, let's call that P and let's call that Q. So any other random point on that line, I'm going to call x, y, and z. So that can be any point along this line here. Well, how could I represent this? Well, one way to think about a line is really just a whole bunch of different length vectors kind of laid on top of each other. So if I had another vector down here, let's call this vector, I don't know, u, and that's going to be a, b, and c. If this vector u points in the same direction of this line, then if I make a vector between the point on the line and any other point, then the vector pq would have to be just a multiple of this, right? If this vector here, if I made that vector, since it points in the same direction, it just means it's just this vector of a different length. That means that would have to be some constant multiple, some multiple of u. Now I'm using the letter t here because q here is an arbitrary point. It could be, closer or farther away, which means that t can be a bigger or smaller value for this. Well, this relationship right here actually tells us how to write the equation of a line in 3 dimensions. Because PQ, if you do the vector PQ, that would be the vector x minus x naught, y minus y naught, and z minus z naught. We said u is pointing in the same direction as our line here, so I'm going to go ahead and put in just the random a, b, and c that it would be. So that would be t times a, b, c. So that means that x minus x naught, y minus y naught, z minus z naught has to be equal to at, bt, and ct. Well, for 2 vectors to be equal to each other, their components have to be the same. What we end up with here then is 3 separate equations. So this is something that is completely different than in 2 dimensions. To represent a line, we actually have 3 equations. So we get x minus x naught is equal to at, y minus y naught is equal to bt, and z minus z naught is equal to ct. Or, if I just go ahead and solve for our random point x, y, z, so any point on the line can be given by at plus x naught. The y value is bt plus y naught, and the z value would be ct plus z naught. Okay, this is how we write the equation of a line in 3-dimensional space. This is called a parametric set of equations. So to write the equation of a line, we actually don't get a single line, or a single equation. We get 3 equations to represent that one line. Good news and bad news here. Since our vector u here, this a, b, and c is just a direction vector, this vector could have been any length to start with, which means a, b, and c could be different values and it would still work. Which means the a, b, and c here aren't unique, which means those could be completely different. And since there's lots of points that lie on this line, this x naught, y naught, z naught that we picked, the point that was on the line, can also be different. So these aren't unique. These are not unique equations. That's good news and bad news. The good news is you can have a lot of different combinations to represent the exact same line. The bad news is you may not end up with the same equation the back of the book has, but most of the time it's going to be pretty close. Now this is called the parametric set of equations for a line. There's another way to represent these, and it's called the symmetric form. All right, all we do for the symmetric form, instead of solving for x, y, and z here, what if we solve for t in all of these? That means that t would be what? X minus x naught over a. T is also y minus y naught over b, and t would be z minus z naught over c. Well, if that's what t equals, and t is the same thing, that means all three of those would be equal to each other. So the symmetric form of a line is x minus x naught over a equals y minus y naught over b is equal to z minus z naught over c. That's called the symmetric form of a line. Generally, what I would tell students is always come up with the parametric set first, then solve for t to get it into the symmetric form. Generally, it's far less useful than the parametric form, so that's the one we're going to stick to most of the time. All right, so let's say if I said, find the parametric and symmetric equations for the line that passes through, let's say, 1, 2, 3, negative 5, 3, and 1. All right, so just like in two-dimensional space, there's only one line that goes through 2 points. So the 2 points define a line here. So here's what you're thinking. To write the equation of a line, so let's go ahead and stick this here real quick underneath here. To write the equation of a line, you need a point on the line and a direction vector. Now notice I said a direction vector, not the direction vector, because any vector that points in the same direction as the line will work. Now, if we know we need a point, this x naught, y naught, z naught, and a direction vector to give us the a, b, and c, what information are we given here? Well, we definitely have a point, so either one of these points would work. We need to find a direction vector. Well, since those 2 points are on the line, right, there's a point and there's a point, a direction vector would just be a vector that points from one to the other. So for our vector, I don't care what letter you use, I'm gonna call it u. So our direction vector is going to be what? 1 minus 5, which would be 6. 2 minus 3 is negative 1. 3 minus 1 would be 2. This is our direction vector. Okay, once you have your direction vector and a point, you're basically done with this problem. So one set of parametric equations would be 6t plus, I'm going to use the first point, 1. Y is equal to negative t plus 2. Z is equal to 2t plus 3. Notice the 6, negative 1, 2 is my direction vector, and I use the point 1, 2, and 3. This would have also worked if you would have used the second point, negative 5, 3, and 1. To make it even more confusing, it would have worked with any multiple of this. So you could have multiplied this by 2, and you got 12, negative 2, and 4 would also have been correct. So the way that you're going to check these in your homework is the direction vector that you use should be either the same one or a constant multiple of the one the author used, and the point is generally one of the given points, so one or the other would work here. Now that's a set of parametric equations. The symmetric form is basically just plugging into the symmetric form. So that would be x minus 1 over 6 is equal to, where am I at? Y minus 2 over negative 1 and that's z minus 3 all over 2. So here's our parametric form for the line, and there's our symmetric form. Again, I'm just plugging it into the formula. So lines are fairly easy to draw as long as you know a direction vector and a point on the line. You always need at least a point on the line. All right, so lines are pretty straightforward as long as you have those two pieces of information. Let's take a look at planes. Now, a plane is generally defined by 3 points. So think of the board here, right? If you just have 1 point, there's an infinite number of planes that go through that. If you have 2 points, you've nailed it down a little bit more, but there's still an infinite number of planes that can rotate along that as an axis. But as soon as you put the 3rd point there, that pins down a plane. Now, we also saw from our cross product lecture that 2 vectors also define a plane because, well, to come up with 2 vectors, you need at least, or 2 unique vectors, you need at least 3 points. So 2 vectors also define a plane. So how can we come up with the equation here? Well, let's say this. Let's say I know a point in the plane. So I know this point, the x naught, y naught, z naught. I know that that exists in the plane. If I were to pick any other random point in the plane, well, let's call this one just x, y, and z. So that's just a random point in the plane. That means that there has to be a vector that connects the two. Well, if the vector if the number x, y, z actually lies in the plane that we're talking about, then this has to be true. Remember, the normal vector to the plane would be kind of, the way I have it drawn here, would kind of be coming out at us. If this really lies in the plane, that means that these 2 vectors lie at 90 degrees to each other, or they're orthogonal, which means that the dot product between the normal vector to the plane and point in the plane and any arbitrary point has to be 0. So just like I did before, if I call this some point P and this one Q, doesn't matter which one's which. And I were to find the vector PQ, if I dot that with the normal vector, it would have to be 0. If that point really is a point in the plane. So let's say our normal vector again is the vector ABC. And PQ is exactly what we did last time. That would be x minus x naught, y minus y naught, z minus z naught. Well, we know for it to be in the plane, the dot product between those 2 would have to be 0. So PQ dot n, which would be x minus x naught, y minus y naught, z minus z naught, dotted with ABC has to be 0. Or if we do this dot product, A x minus x naught, B y minus y naught, plus C z minus z naught has to be 0. Well, believe it or not, that's it. There is the equation of our plane. Now the good news here, compared to our line, this is actually unique. The reason that it's unique is because technically there's an infinite number of normal vectors, right? Any vector that points in that direction but is a different length. Well, all those different ones are just constant multiples of the original. Now, since this is an equation this time, a single equation, I could always multiply through or divide through by a constant, which means that this A, B, and C can always be reduced to the same value. So the equation for a plane is unique. But what would we need to write the equation of a plane? Well, what did we use to come up with this? We need, so to write the equation of a plane, we needed a point on the plane, and a normal vector to the plane. All right, this is good news and bad news. They're generally going to give you a point, but to find a normal vector, that's going to take you some work a lot of times. Remember, to find a normal vector, the only way we've been able to find a normal vector so far is the cross product. So let's come over here and try an example of this. So let's see, find the equation of the plane. Of the plane that contains the points, I don't know, 1, 2, 3, 4, negative 2, 1, negative 2, 1, 3. Okay. So here we go. We know that these are 3 points, so these should define a plane. So what do we need to do this? Well, to write the equation of the plane, we need a point on the plane. That's good, we got plenty of those. And we also need the normal vector. So the idea here is we have 3 points out there. The easiest way to do this is to find the vector between, I don't know, P and Q and P and R. Something like this, I don't care. Basically, if we just call these P, Q, and R, whatever, you don't have to name them. I'm going to find the vector between P and this one and the vector between those two. And that'll give me my 2 vectors that I need to do. So the vector between P and Q, P and R, again, I don't care which order that you do these in. I'm going to do P minus Q. So 1 minus 4, 2 minus a negative 2, 3 minus 1. And then I'm going to do the vector between P and R. So 1 minus a negative 2 is 3. 2 minus 1 is 1. 3 minus 3 would be 0. So again, from the kind of the picture, we had 3 points out there. What we've done is we've made 2 different vectors. Remember, we got to find the normal vector. So I'm going to do the cross product to find a normal between those 2 vectors. So let's go down here. So I'm going to do PQ cross PR, I, J, K, negative 3, 4, 2, 3, 1, 0. I'm going to give myself a little bit more room here. I remember how we did this. In the I direction, that's going to be 4 times 0, which is 0, minus 2 times 1 is 2 in the I direction. Minus in the J direction, that's going to be negative 3 times 0, which is 0. Minus 2 times 3 is 6. And in the K direction, that's going to be negative 3 minus 12. Now, I did that rather quickly, so if you're still not real good with these, make sure that you're practicing your cross product because it's never going away. All right, so that gives me negative 2i plus 6j minus 15k. Or if you prefer the bracket notation, negative 2, 6, negative 15. Okay, so now we have everything we need to write the equation of this plane. So I'm going to put it back up here real quick. Remember the equation of our plane? That's wrong. Is ax minus x naught plus by minus y naught plus cz minus z naught is equal to 0. A, B, and C here, that's going to be our normal vector. So this is, in case you want to remember, that's our normal vector. So in any point, I'm going to use the first point up here. So you get negative 2x minus 1 plus 6y minus 2 minus 15z minus 3. Now it's fine with me if you leave your answer just like that, but the book is almost always going to distribute everything out and move the number to the other side. And once you do that, your equation should be exactly what the back of the book has. All right, so writing the equation for a plane, you need 2 things always. You need a point on the plane, the x naught, y naught, z naught, and you need any normal vector to the plane, a, b, and c. All right, let's take a look at one super quick topic to finish this up. All right. All right, we've taken a look at angle between 2 vectors before, but how do we find the angle between 2 planes? Well, the pictures are kind of hard to draw here, so I'm going to draw a very simple picture. You're going to have to use your imagination here. Imagine that those are 2 planes and we're looking at them kind of on the edge of the planes here. The angle between them, well, if you look, there's technically 4 angles between them. 1, 2, 3, and 4. So which angle are we talking about? Well, angles that are directly across from 2 intersecting lines are called vertical angles, and they're the same. So that's the same as that one, and this one's the same as the one across from it. So we're really down to 2 unique angles. So which angle are we talking about? Well, just like with vectors, we're always looking for the smallest angle between them. So what we'll be looking for is something right there. So how could I find the angle between those 2 vectors? Well, it's going to be a little bit more difficult to see. Imagine the normal, or a couple of normal vectors to these planes. Let's call that the normal vector 1 and normal vector 2. So those are perpendicular there. Now, you're going to have to help me, use your imaginations. Imagine putting these to where they start at the same spot. So this one kind of looks like that, so that's N2. And this one kind of looks like that for N1. Well, if you rotate this, you would see that that would fit exactly right there, which means the angle between those would be theta. Since N1 and N2 are vectors, we can already use something we already know. We know that the angle between 2 vectors is the dot product over the magnitude of each one of them. All right. This is almost right. Here's why. What is the biggest, the smallest angle between 2 planes can be? Well, when the first time I asked you that question was, what's the biggest 2 angles, or the smallest angle between 2 vectors could be? And that's actually 180 degrees if they're straight across from each other. But if we're talking about 2 planes, the smallest angle can be is actually 90 degrees because they would be perpendicular planes kind of looking like that. If you rotate it any more, right, we kind of rotated it that way. If you rotate it any more, then the other one would become the smallest, and that would be less than 90 degrees. So to make sure that this gives us the right answer, what we need to do is make sure that this dot product is positive, or basically that angle falls in the first quadrant, which would be an angle less than 90 degrees. So the only thing we're going to do to modify our formula is put the absolute value on the top here when you're finding the angle between 2 planes. Other than that, it's the exact same thing as finding the angle between 2 vectors.